Hi, I'm Si Ben-Yaakov. This presentation is entitled Fundamentals of Silicon MOSFET Losses and Thermal Cooling in Power Electronics System. This is a part 3 of a 3-part series, and this part is dealing with cooling. There are some relevant videos to the subject matter of this presentation. They are sort of providing much more information, and here are the links, and I'm going to print the links on the page of this video that you are now watching. So what is the story of cooling? If I have a mass and I bring in some energy into it, then I'd expect a thermal rise. If this energy is converted to heat, as it will be, say, when a current is passing through the resistor. And this process is related, or the amount of increase in temperature is related to the thermal capacity of this body, which is defined as energy pumped in over the change in temperature, and this will be in joule per degree centigrade. Or it'll be specific thermal capacity, and this will be per gram. Now, here we have the ambient temperature, the surrounding air, let's say, and therefore there's going to be a movement of heat from this unit, which is at a higher temperature, toward the ambient. This removal could be either by radiation, which is usually very small, and primarily by convection. That is just moving the heat by contact, you might say, and in this case it'll be like to the air, to the surrounding air. Now, the parameter related to this process is the thermal resistance, and this is the temperature drop per power passing. This is degrees centigrade per watt, and this will be the temperature drop between the surface here and the surrounding. Okay, this is the delta T. And if I'm going to add some airflow, this will improve very much the convection, and this will actually reduce this number. So this number could be reduced and improved. That is, we'll have more heat moving out if we can have an airflow passing the surface. In order to get better heat removal, we would like to enlarge the surface. This is the tab of, say, a transistor T220. This is a metal tab here, which is, by the way, connected to the drain, which is not that important in the connection of cooling, but this will require some isolation in many cases. But anyhow, we have here a metal part which is getting hot, and in order to cool the unit, I can actually connect it to a heatsink. In this case, it's just a flat metal, say, which the unit, the transistor, is screwed or bolted to it. And the surface here is much larger, so therefore we have a better convection. Now, in this case, we're going to have three, in fact, thermal resistances. One internally in the transistor between the junction and the case. This is given in the datasheet. And then between the case and the heatsink. If you use some insulation, then we have to take it into account, this thermal resistance of the insulation. And then we have the thermal resistance between the surface of this simple heatsink and the air or the ambient. Of course, in order to improve the thermal removal, we'd like to put a better heatsink, one with fins, which is increasing considerably the surface area and therefore reducing the thermal resistance between the heatsink and the ambient. So in this case, we're going to have the junction to case thermal resistance, case to the heatsink thermal resistance, this will be the insulation, and then the heatsink to air or to the ambient. What I'm showing here is an equivalent circuit, an electrical equivalent circuit of the thermal parameters. In this equivalent circuit, the emulation is done by representing thermal power by current, temperature by voltage, and thermal resistance by resistors. So this represents the ambient temperature. This is the temperature of the ambient. It's a fixed temperature. This is the thermal resistance between the heatsink and the ambient. This is between the case and the heatsink, and this is then we have the thermal resistance between the junction. This is the temperature of the junction here and the case. Now you can find then the temperature of the junction if you know what is the power, which is now current, represented by current passing here, and the voltage drop on these resistors plus the ambient temperature. This will be the junction temperature. Now this is for the steady state. In the transient, which I'm going to talk a little bit of later, we have to take into account the specific heat capacity or thermal capacity. We have an internal within the device itself, and this sort of represents the heatsink, which is a very large mass here, so the heat capacity here is much larger. So if I have a transient phenomena, say a step or a short pulse, one has to take these into account. Now the junction to case thermal resistance of transistors is depending on the size of the transistor, the area of course, that of the pad. This is the surface which we attach to a heatsink. And for very small transistor, we're talking about 20 degrees centigrade per watt, or higher than that even, if it's a small transistor. And then large, say, MOSFETs, it's like 247, T247, it would be like 0.5 degrees centigrade per watt. Now, the isolator typically will be in this range, like 0.5 to 1 degrees centigrade to watt. And then the heatsink itself, depending on the size of the fins, and obviously it's a function of the airflow, whether it's still air or there is an airflow, could be in this range. So let's take an example. If I have a transistor which the power loss, the total power loss is say 15 watt, and we allow 110 junction temperature, and say the ambient is 50 degree, and then the junction to case of the transistor is 1 centigrade per watt, and the insulator, this is from the case to the heatsink, is also 1 degree per watt. So what is the thermal resistance of the heatsink required in order to assure the 110 junction temperature? Well, this is very simple. I'm going back now to the equivalent circuit. Here it is. Here we have all these three. We are missing this one. We know the ambient, so the ambient plus the power, which we know, times all these resistances is equal to 110. And this is what we have here. This is the power, total thermal resistance, and we can solve for the heatsink that we need 3.6 degree centigrade per watt heatsink, which is a practical heatsink that one can consider. Now we can put transistors in parallel to improve two things. One is obviously if we have two transistors of a given RDS(on) and we put them in parallel, then we have an assembly with half the RDS(on), if these are two transistors, could be more. And, which is also very important, we are getting a larger surface area. So the effective, you might say, thermal resistance is also halved. So this is why, in many cases, it's better to take two transistors or more rather than one with a smaller RDS(on). Sort of spread the heat among the various transistors which are connected in parallel. So this could be a motivation to use a number of transistors in parallel, other than the fact that they are reducing the effective RDS(on). Now what about thermal transit? If the power is not constant, say we have a step, then obviously you would expect the temperature to go up and then eventually to stabilize. Now if we look at the very simple equivalent circuit taking into account the thermal capacity, then we realize that we have a time constant here which will determine this rise of the temperature. Now in reality there are a number of time constants, but if you have a heatsink, then a major one will be associated with the thermal capacity of the heatsink. So if we have a number of pulses, then the temperature will go up, and then it will cool off sort of through this thermal resistance, and then it'll go up again. So we can calculate this knowing the capacity, the thermal capacitance and the thermal resistance, and we can actually solve for this case. I'm assuming that these time constants are much larger than that of the transistor itself. So here is a way to get it in a more complex situation, which is very difficult to calculate by hand, if not impossible. This is done, or could be done, by finite element analysis, a thermal simulation, in which actually the program is breaking down the volume here. This is a 3D, three-dimension simulation, breaking it down into small cubicles, and then solving for each one of them the thermal equation, connecting them by the surface values. So here is a case, and here we have a block of aluminum to which the transistor, so these are say TO220 transistor, which are attached to this block of aluminum. Obviously, we would need normally a insulator here in between. And in this case, we have 15 on one side, then 15 to other side, and this is attached now to a plate, no fins here, and the thermal convection is done by the surface here, and also a little bit here inside. This is inside the box, so it's less effective. This is from the outside for the transient. Now here we see the steady state situation. Here on the transistor, we see the hot spot here. There is a gradient here. It's very small because this is aluminum, so the heat conduction is very good. So there's only 3 degrees between the coldest point and the warmest point. This is again steady state, and in this case we have 79 degrees here on the surface, and of course we can calculate what is the junction temperature, knowing the thermal resistance between junction and case. So this is a steady state, and this is the transient. That is, here we started to pump in the power, and the temperature, this is temperature now, start to go up from about 25 degrees, which is the ambient, to about this steady state value, which is about 78, 79 degrees. Now, the time scale here, as you can see, this is 40 minutes, and this is 166 minutes. So the time constant is very large because the heatsink has a large mass here in this particular case. So the equivalent circuit, the first approximation, is something of this nature. This will be then the thermal capacity of the heatsink, of the aluminum blocks, and this will be then the thermal resistance between the surface to the ambient, and here we have the ambient temperature. Now, the time constant, as I've said, can be found from this curve here. It's about 63% out of the maximum, which is about 1 hour. So it'll take like a couple of hours to stabilize. And this is for a given power level. Now, obviously, if I pump in a higher power level, this will go much faster. But before that, let's just have a look at the expression here. This will be the typical exponential increase in a RC circuit. This is the final value, and this is now the time constant, the product of these two. So if now the power level will be like 2.5 times larger, then obviously this will go much further. Here it's about a straight line, so I've approximated it to a straight line, and the slope is the power over Ct. And as you can see here, this will reach, of course, the final value that we want, or that we would allow, in a shorter time, in this case 25 minutes. Now, this would mean that this system, for steady states, would be able to handle this amount of power at P1, but for a short period of time, the system will be able to handle much higher power. So suppose there is a pulse of, say, 1 minute, then the power that can be handled will be much larger. So this is again a output of the 3D thermal simulation, which, as I've said, is a very powerful tool because otherwise it would be almost impossible to see all these details. So this brings me to the end of part 3, which is the last part. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.